Hello everyone. In this particular video, we are going to learn some basic syntax structure of Verilog. What are the syntax rules followed in Verilog? What are keywords? What are identifiers? How we write numbers in Verilog? What a module in Verilog is? So starting with syntax tokens in Verilog. So what exactly is syntax tokens? Let us say you are going to write a code where we have written C equal to A plus B. So in this, when this whole line is processed in compiler, what compiler does is it breaks down each and every detail of this code into different tokens. So this one is also a token, this equal to is also a token, this A is a token, plus is a token, B is also a token, and this semicolon is also a token. So then these tokens are processed further to provide us the results. So what we are going to see over here is what are different types of tokens in Verilog. So what we are having white spaces. If you want to insert white spaces in Verilog, we see how in between a code if you want to insert white spaces. Then we see how we insert comments. Then we see what our operators is. For example, we have written C equal to A plus B. So over here the operation between A and B is happening is we are adding them. So this is a plus operator. Then what we are doing, the sum of A and B we are assigning it to C using this assignment operator. So this is also operator. Then we are going to see number specification, how we are going to write numbers in Verilog. Then we see what exactly a string. In Verilog, string is actually a group of characters enclosed in these two double quotes. Then we are going to see what identifier in Verilog. Then what are keywords in Verilog. All things will be covered in detail, no worries. Then we'll be starting with Verilog syntax. So in Verilog is a case sensitive language. When we say case sensitive, that means these two and this is in uppercase, this is in lowercase. So these two both will be treated as different in Verilog. Then what is a keyword in Verilog? A keyword is a reserved word. Keyword is a reserved word in Verilog which is used for some specific purpose, I would say, to be more precise, purpose, to be more for some task, right? For some specific purpose, some reserved words are there. Those we call keywords. Keywords are always written in lowercase. These are actually the words which are being used by language to define its specific purpose and some specific task and functions. For example, when we say module, what exactly a module is? This module is a keyword. What this keyword will do is it will create a block of design. Under this block you can make your design whatever you want to make. So module keyword will make this design. Initial will do what is, initial is also a keyword. There is some block of code. This is a block of code. Initial signifies the start of this block of code. Similarly, always also signifies the start of a piece of block of code. What is the difference and all that we'll be seeing further ahead. Then begin and end. In other programming languages you might have seen we use curly braces, but in to start a code block and end it. But in Verilog what we use is, we use instead of these curly braces we use begin and end. So in between you can write the code. Then case, wire, while and module, this all will be seen. So the keywords are some specific words which are used by language for some specific purpose. Then we are having identifiers in Verilog. What actually a identifier is? Let us say we are having a design. In this design we are having some different modules, small modules, and some wires which are connecting them. So to name these wires, to name these modules, let us say A, B, H1, B2. So how we are going to assign these names to identify these modules? There might be a possibility that these two functionalities are same, but we want to name them differently as we are using them twice. So we assign some names to the objects in Verilog. That is what we call identifiers. There are some rules for the identifiers. One of the rule is the name of identifiers can contain only alphanumeric, that is A to Z, 0 to 9. It can contain underscore and can contain dollar sign. Identifier name can't be started with numerical and dollar characters. We'll see the example. See, this is my underscore variable, this is valid, my underscore variable 1, this is numeric also include, underscore also include valid, then my underscore variable dollar, this is also valid. Then we are having, see, this starting as numerical, this starting as dollar, so this is invalid, these are valid. As we have said, the name can't be started with numerical and dollar characters. Then we are having this example, for example, reg value. So this reg is a keyword in Verilog which is used to make a register. So it will make a register, and this value is what? It is the name given to this register. So this is a value, so this is the name of this register. So this value is what? Identifier, as it is identifying this register, and this reg is what? It is a keyword, as it is performing some specific purpose in Verilog. Similarly, we are having input and clock. So this input is a keyword and this clock is a identifier. So the comments in Verilog, how we write comments in Verilog? So comments are written as, there are two ways. If you are having a piece of code written like this and you want to comment only this line, so you will put two slashes, forward slashes in front of this line. And if you want to comment all these lines at once, what you will do is, all these lines, what you'll do, you'll, instead of this, you'll write this one slash, one asterisk, and at the end one asterisk and one slash. So all these lines will be commented. Further ahead, we are going to see white spaces, how we are going to insert white spaces in Verilog. So one escape character, when we say escape character, means it will bypass whatever is written in place of it. What exactly I mean, you will get to understand when I explain this particular example. So as of now, understand this thing, that whenever there is a backspace n, so actually these are the characters, special characters, which are used only in strings. So what exactly is a string is, it is a group of characters. So when we write \n, it will insert a new line character. What exact? Then if we insert backspace t, it will insert a tab character, that means 5 spaces it will insert. Then we have backspace b, \b, what it will do is, it will insert a blank space. It is not a blank space, it is a backspace. So all three will get clear with these examples. If we are having this hello \n space world, so what it will be visible at the output is like, so this hello world at output, how we are going to see this is, in output you will see this as hello, and then in next line it will print space world, right? So what \t does is, it will be printed as hello, and then 5 spaces it will insert. 5 spaces for T, and 1 space after T is there between world and T. So 1 2 3 4 5 and 1 space of before W. So and then it will print world. What this backspace backslash B will do is it will make the cursor go backspace once wherever this character arises. For example, at first it will print HELLO. Then what will happen is the backslash B has arrived, so it will go backspace once. Then what it will do is there is one space after backslash B, so we press one space, then the world will be printed. So this is how all these three special characters works. Then we are having how we are going to write numbers in Verilog. So there are two types of numbers can be written in Verilog. One is sized, one is unsized. So what is sized? That means the number of bits that particular number is going to take, you already provide it, you write it. And in unsized, you don't write the size, you don't write the number of bits needed to store that number. For example, the syntax for sized is first you write the size, then you write the base format, then you write the number. When we say base format, in which format you are writing the number? Your number is decimal, binary, hexa or octal. With example it will be more clear. For example, we are having the sized numbers. So in sized numbers, if you see 4 tick B, this 4 is the size, that means you want 4 bits. Then we are having B, that means the number will be in binary. Then this is the number, 4-bit number, right? So this is also similar, as you can also write it as 4 tick B. What exactly this is in binary? 1011. That means it is what? It is number 11 in decimal. So what you can do like this, you use 4 bits you want. Instead of B you can simply use D. That means in decimal you are going to write the number, and you can simply write 1 1, that is 11. So what it is this, and 4 tick B 1011, these both are same. This is only two different ways of writing. This is in decimal and this one is in binary. Similarly, over here it is a hexadecimal number, 12 tick H, and this is the hex value. Then 16 tick D, then 255. The 255 will be stored in 16 bits. Then we are having the unsized numbers. In unsized number, if you see, there is no size defined. So how the size is being taken in this case? It is 32-bit. How 32-bit? It is system default. Whatever the system default bits is, it will be taken by the compiler. For example, 2 3 4 5 6. So this number will be stored in a 32 as a 32-bit number. Then tick HC3, as it is unsized, it will also stored as a 32-bit hexadecimal. Why hexa? Because this is H. If you don't define any format specifier, it will automatically take it as decimal. Then tick O, that means this is the octal one. There are some important concepts which you can use for your readability. For example, underscore you can use in the numbers. 32 tick H A underscore B underscore BC underscore 1. This is also same like this, or it might have written like this: 32 tick H A underscore B C underscore 1. And if you remove this underscore, it is A B C 1. So these both are same. Or this might have written as like 1010 1011 11000001. But the thing is, see how hard it is to read it. but it is easy to read this. So underscore increases the readability. There is one more concept of extension. If you have written it as 4 tick b, then 1, so whatever the remaining 4 bits are, if there is nothing, those will be populated with 0. If there is x already there, so the other remaining bits will be populated with x. If it is z there, the other remaining bits will be populated with z. So this is a bit extension concepts in number. Next we are going to learn is what exactly is a module. This is very important in case of Verilog, because everything in Verilog is there in terms of modules. So when we design any design in Verilog, at first the design is there to be encapsulated in a module. Then you put some functionality of the design, you write what this module will do. The module is having some inputs to it and some outputs to it. So this is the design which is having some inputs, it is having some outputs, and this design will perform some function. So how exactly this is written and in code, how the module is made, we see. So at first we start with writing the name module. So this is a keyword which says that it is starting a module. So when it is a module, so what happened is, and this is AND module. So between these two you can write the whole module functionality. So module and AND module, this is begins the module, this ends the module. So what exactly it develops is, it develops a module type space. The module and AND module has developed this particular thing over here, this one. Then what is AND gate? So what exactly is this? This is the identifier, this is a name given to this particular module. So this is a AND gate, the name of this module. Then what we are doing is, this is the first way of defining the ports of module. There are two ways, second one we are going to see also. So what is in this first way is, we are defining the direction, that is input and output, and the ports in the same module declaration. See, this is a bracket of module which is getting terminated over here. So what we have is input A, there is input A, input B, there is one input B, and one output Y. Then after this semicolon, the module declaration has been completed. Then comes whatever you want to perform inside this particular module, that functionality we are going to write over here. So what we write is, assign Y equal to A and B. So what it says, do AND of A and B and assign it to Y. So A and B are our inputs. What needs to be done? AND of them. So one AND gate will be used. A and B are inputs to it, and it will be assigned to Y. So this is the AND gate module formed in Verilog. Wherever you see a semicolon, it says the termination of this particular statement. Then here you see the direction declaration and the port declaration in two different ways. This is module, this is the identifier. If you see over here, we have defined the module ports. So there are 3 ports to module, but till now we don't know which one is input, which one is output. So it is having A, B and C as 3 ports. Then semicolon, the module declaration has been completed over here. Then what comes is, we are defining the direction, then A and B are inputs and Y is output. Then we are defining the functionality, Y equal to A and B. So this same structure will be realized using this code. Next we are realizing a half adder, using how a half adder module is there. Then what we'll be doing is, we'll realizing a full adder using half adder. Means we will be develop a half adder module, then we'll develop one full adder module, and we'll use this half adder module, 2 half adder modules in this bigger module. This is full adder, these are half adders, 2 half adders. How to achieve this? we'll see over here. At first, module, that means a simple module. Then what we are having over here is half adder, the name of this module, half adder. Then input A, input B, output sum, output carry. A, B, sum and carry. Then this is module declaration ended over here. Then we are writing the functionality. What functionality is? Assign sum as A XOR B. So we will be having a XOR gate A and then XOR B and assign it to sum. Then we are having one more statement. See, there is semicolon, that means this statement has been terminated over here. Then assign carry with A and B. So we need to perform AND of A and B. So what will be done? AND of A and B and assign it to carry. It is assigned to carry. So this is the half adder, which is the code of this half adder is written like this. And then at last AND module. Next we are going to use this half adder which is generated in our full adder. So the code of full adder goes is, at first we are having a module block will be created. Then one second, one module named full adder is created. Then there are inputs A, B and C in. A, B and C in inputs, sum and C out output, sum and C out as outputs. Then what we are having is, we have got declared 3 wires. This wire keyword will declare 3 wires. Think of it as like simple wires which are used to make connections S1, C1 and C2. We'll be using these wires in our half adder module to connect these two half adders. So one is half adder HA1. So this is HA1 half adder, HA1. What HA1 it does is, what our half adder is having A, B, sum and carry as its ports. So what is A, B, then sum and then carry. So what it is doing is, it is applying the A of half adder with A of full adder. So that means A of half adder it is there, A of full adder it is there, we are connecting them. Then the B of half adder with B of full adder, B of half adder with B of full adder. So this is being connected. Then sum of half adder with S1. So what S1 is? This was the wire which was declared. So sum with S1. So this was the wire. Then carry with C1. This carry with C1 wire. Right. Next what we are having is, we are having one more half adder, that is HA2. So there is one more half adder, HA2. So this is a copy of the same half adder module, which will be having A, B, sum and carry. So see, the A of half adder 2, this A is being assigned to with S1. So where is S1? We are having S1 over here. So the A is connected with S1, right? Next we are having the B of half adder 2 is connected with C in. So where is C in? The C in is connected with B. Then we are having the sum is connected with sum of full adder. So this is sum of half adder is being connected with sum of full adder, something like this. Then what we are having, carry which is being connected to C2. So this carry connected to C2, where C2 is, this was the wire which was developed, used in declared over here. So carry is being connected to C2. Now what we are having at last is we are assigning the C out with C1 or C2. So what we are doing is we are doing OR of C1 and C2. So we needed a AND gate, sorry, OR gate. We needed a OR gate. This C1 is applied and C2 is applied to it, and it is assigned to C out, and then AND module. So what exactly we have performed is we have achieved this particular design using this half a full adder code. And in this, if you have seen, we have used two half adders which we have generated using this code in this full adder. So see the module functionality, this half adder was a module, this was also a module, and this full adder is a bigger module. So in Verilog, how things works is we build up things in simpler modules, then we combine them to build bigger module. So this is how structural hierarchy is there in Verilog. Next we will be learning is the data types in Verilog. What types of data types are there in Verilog? For example, this wire, this was a data type which we have declared this S1, SC1, C2, right? So the things will keep on getting clear when you move ahead, when you learn few more concepts. So if you are having any doubts, feel free to ask in the comment section, and keep learning, keep supporting. Thank you all.